Okay, welcome to the Henstitute. We're going to try to take a look at another compound circuit here. I went ahead and put some stuff over here to the side so you can kind of see what exactly we're going to try to find. We're going to try to find the total resistance, the total current, find the currents through each one and the voltages through each one, and see what we can kind of come up with. So that is the plan. The first thing is you notice that we have a battery over here. It's a 24-volt battery. If you really care, the positive side would be this side, the negative side would be that side. So really, if we were trying to think about this, we would say the current is coming from the positive side, so this is going to be our current. And if you notice, the first thing it's going to run into is it's going to run into resistor 1. So it has to go through resistor 1. There is nowhere else to go. So what we actually find is that I1, the current through that, will actually be equivalent to the I total over here. And then it's going to eventually come around and it's going to reach this little junction. So some of it's going to go this way, some of it's going to go this way, some of it's going to go through this resistor, come back, some of it's going to go wiggle, wiggle, wiggle through this resistor and come back. They will combine back together into the total current, and then they have to go through here. So they have nowhere else to go, and then eventually come back to mom and dad battery. That will be our total up here. So when you think about this, even though it looks like R1 up here, the 2 ohm and the 4 ohm, you might say, hey, those look like they're in parallel because those two lines are parallel with each other, but you're following the current. You're thinking of the current. This R2 over here and this R3 are the only ones that are actually in parallel with each other. The other ones are in series with that. So when we start this out, the first thing we're going to try to do is find the equivalent resistance of a 3 ohm resistor. So combine this in there and this 6 ohm resistor. So the RAR method, we'll take the reciprocals, we'll add them together. So this is like a 2, 6, add that together, that's going to be like 3, 6, flip that over because you got to take the last part of RAR and get 6 over 3, which is 2 ohms. So this entire setup looks like a 2 ohm resistor for the R2 and the R3. Then we can combine the R1, which is 2 ohms. In here, it is in series with this R23, which is the 2 ohms. And then it's in series with the R4 down here. So we'll add the 4 ohms. 2 plus 2 plus 4 is 8 ohms of resistance. So that's our total resistance. Now we are ready to actually find the total current coming out of this thing. Here, let me see if I can move this out of the way. Sorry about that. So our total resistance here is going to allow us to find this total current, because the total current over here is going to be my 24 volts, the total voltage, divided by this equivalent resistance, which is 8 ohms. 24 over 8 would be 3 amps of current. Yes, 3 amps of current is coming out of this battery. 3 amps of current is going to first run into R1. So if it runs into R1, how much is going to go through R1? All 3 of those amps are going to go through there. There's nowhere else for them to go. So this resistor, this I1, is the same as the total. It's 3 amps. It's only when it reaches this junction over here that it's going to split. So we're going to get some of it to go to the 3 ohm and some of it to the 6. There's 2 ways to do this. One method is to actually think about how 3 and 6 are related to each other. Since 6 is twice as much resistance as 3, we should get half as much current. So I need to split the number 3 into 2 numbers where one is twice as big as the other. And sure enough, I can split it into a 1 amp and a 2 amp. And those add up to 3. Eventually that 2 is going to come back together with the 1. And guess what? We have the 3 amps of current that are going to go through this resistor right down here. There's only one path because 3 amps has to get back to our battery. So I4 was also going to be 3 amps. And these two added together would be 3 amps. And we figured out that it was going to be 2 amps through here, and 1 amp through there. That's one way to do it, but what if you couldn't see a pattern between 3 and 6? Is there another way to do it? The other way to do this is to go after all these voltage drops. And the way we think of these voltage drops is how much money we're spending. Remember, they're going to take off, and I always did this. I drew my money. They're taking off with their 24 volts here. So as they travel around, they're going to come to this resistor. Since all 3 amps are going to go through this 2 ohm resistor to find the voltage drop on V1 here, we're going to take I1 times R1. So we're going to take our 3 amps and multiply it by the 2 ohms. And 3 times 2 is 6 volts. So this is going to use 6 of our volts here. They had 24, they used up 6, so they dropped 6. So afterwards, when they're on this side of it, they're actually going to only have, if I take 6 away from 24, they're going to have 18 volts left. When they come down here, whether they go this way or that way, they're going to carry that 18 volts. I'm not going to say anything about it, and then eventually they're going to come back. We don't know how much, but I'm going to come down to this. I'm going to find how much voltage we drop down here. What is V4 down here? They like to write it as a delta V in this. It's just a voltage drop, but I'm just going to leave it as V. So either way, you can do it delta or just V. So it's going to be my current, 3 amps, multiplied by my resistance of 4 ohms. 3 times 4 is 12. So this is going to use up 12 volts down here. Now, if you remember, that had to spin the rest, because when they come back to mom and dad battery, they have to come back with 0 voltage. They got to have nothing. So along the way, they spent 24 volts. So they spent 8 of it down here. They spent 12 of it on R4. So if I take 8 and 12 away, that's a total of 20 from that 24. If I take 6, sorry about that, and 12 away, that's 18 volts. So how much did they spend on this little section right in here? Well, the amount that they spend in that little section down there is going to be whatever the difference is. So we've got to take 6 plus, I'm just going to call it X for right now, plus 12. All this has to equal 24. And so when I add that up, I find out that they have to spend 6 volts in this little section. So they have to spend it. Doesn't matter which way they go. If they go over here, they have to use 6 volts. If they go over here, they have to use 6 volts. So the voltage across these 2 different parts are going to be the same. So these 2 are the same voltage. This is another way to do it. And 6 plus 6, and now it's not going to be an extra 12, but 6 plus 1 of these, 6 plus 12 gives me my 24, because you're going to go only one of those paths. And so this is another way to see it. Sure enough, if I take 2 times 3, do I get 6? Yes, I do. If I take 1 times 6, do I get 6? Yes, I do. So those are 2 different ways to go about it. I know this is kind of messy, but this is another look at a combination circuit for all my people. And then from here, you can find the power, because we've got current and voltage. We can multiply them together, but we're basically using Ohm's law and the power equation. Hope you enjoyed this edition of the Henstitute, and that pretty much sums up everything in chapter 20. So enjoy.